Namaskar and a very warm welcome to NCERT's live interactive session. I am Neha Tripathi. You're watching us on SWAYAM Prabha's channel Kishore Manch, and you can also watch us on our official YouTube channel NCERT Official. Today we have a session of maths for class 8 where we will learn about quadrilaterals. We'll start with the basics of simple shapes, moving on to complex ones with the help of various tools. To teach you all about quadrilaterals, we have with us Ms. N. Harini. She is joining us from Demonstration Multipurpose School in NCERT's Regional Institute of Education, Mysore. Welcome to the show, Ms. Harini.
Namaskar.
Yeah. We'll start the session in a few seconds. Before that, I want to inform our viewers that if you have any questions related to this topic of discussion today, you can call us on our toll-free numbers 1800111265 and 1800112199. You can also mail us your questions at ciet.kishoremanch@gmail.com, and you can reach us on our official YouTube channel NCERT Official in the comments section. So let's start today's session, and we will take your questions as well. So keep posting us. So Ms. Harini, start.
Hello.
Yeah, Ms. Harini, can we start with the session now?
Yes, I'm ready.
Yeah, please go ahead.
Yeah, welcome children. I hope you are all very safe and sound at your home. So to continue with your learning process, staying at home, I'm here with a chapter on understanding quadrilaterals for you. So what's there in this chapter? You should be very excited to know something about it. So right away through, I'll take you through a concept map which will clearly tell you what all is in store for you in this chapter. So going on to my concept map.
Yes.
I hope my screen is visible to you.
Yes, of course. Please go ahead.
So this is the concept map I have done on the chapter on quadrilaterals. So you can see some nodes here, starting from the quadrilaterals, moving to the left and right. So I'm going to open each of these nodes and allow you to discover what is in store for you in this chapter. So because my central topic is the quadrilaterals, now I'll move on and tell you how we are going to build on this quadrilaterals from some basic shapes that we already know. So we will be starting with simple closed curves. And when we move on with these simple closed curves, we will branch out into two major branches from the simple closed curves, which will be the circles and the polygons. Now why this branching? This is because of the definition that we will be taking up for a polygon. That is, a polygon will be made only of straight line segments, and hence the circles cannot come or get included in the polygons, and hence that has branched out from the simple closed curve as a separate branch. Now once we are ready with the idea of polygons, then we will start classifying them in various ways. The first way in which we will be classifying them will be based on the number of vertices and the number of sides they will have. So specific names will be given to such polygons with specific sides, say be 3, 4, 5, 6, etc. and so on. So we will be giving a nomenclature for all these polygons with specific number of sides. Then from the polygons again, we will be moving out based on their diagonals. We will again get two varieties of polygons, which is the convex polygon and the concave polygon. More about it we will discover when we are into the chapter. Then the third classification which will operate will be based on the sides. That is how they have their sides. Do they have them as equal or they are not equal? Based on that, you will get the regular polygons and the irregular polygons. So this is how it branches out when we talk about polygons from the simple closed curves. Now when we talk about quadrilaterals, we have a family tree which will totally come out of these quadrilaterals, which we shall discuss like this. Like when we have two congruent parallel sides for a quadrilateral, that will be categorized in a special variety called the parallelograms. And when we have only one set of parallel sides, that will be called as the trapezoids. And further from the trapezoids, we will move on to the isosceles trapeziums, etc. Now from the parallelogram, it will be quite interesting for us to see that we will be learning about special varieties of parallelograms. That is, when all the four angles of a parallelogram becomes congruent, we will give it a special name and call it a rectangle. And when they have their sides congruent, the other category will crop up, that is the rhombus. Now from the rectangle, with its properties, when we add an additional property of having all its sides congruent, then we have a special variety of quadrilateral which will emerge. We will keep it on a hold. I'll just come back to the rhombus and see what will happen in a rhombus which has got all the four angles are also becoming congruent. So when I go and discover that, I will end up from a square. That is, from a rectangle as well as a rhombus, I'm going to reach a square. So I'm going to see how special this square is going to be, because it is going to have all the properties of a rectangle and a rhombus. So that is what we will try to establish in the quadrilateral family tree. Now moving on, because we started with quadrilaterals from the simple closed curves, from where we moved on to the polygons also. Because we were talking about polygons, any n-sided polygon will be given specific names, and we are confined to our chapter on four-sided polygons, which we will call it as quadrilaterals. From here, we will move on to the next node, which tells us about any four-sided polygon in specific, because we are going to discuss on the quadrilaterals. So we will be talking about its interior and the exterior angles and the properties related to it. So that is one more branch that we will be looking into. Then from the quadrilaterals, we will be talking about the multiple forms of quadrilaterals, which we have already tried to see in the family tree. But now with respect to their properties, we will try to establish relationships and differences amongst the quadrilaterals. So extensively, we will be talking about their properties. And because we are talking about polygons in general and then more specifically about quadrilaterals, we cannot miss out on the perimeters and the areas. Though it is not included in this chapter for us, but we will be taking up these chapters in the later part of our year. So because the concept map has to be complete, I have just included the perimeter, which is found by a particular algorithm depending on the number of sides the given polygon has. Similarly, when we talk about perimeter, because perimeter is nothing but the boundary, the area also is to be spoken about. And again, here the algorithm or the formula to find the area of a quadrilateral totally depends on what kind of quadrilateral we are going to discuss. So this was exactly the concept map that I made for this chapter. I'll just show you in total how the concept map has grown like this. So we have all this to discuss in the chapter for us. So I hope you are excited that you have so many things all interlinked to each other based on their properties that we are going to study. So I hope I have excited you to that extent that you are going to start the learning with me. So I think from here, now we will go to the simple closed curves, for which I need to share my screen.
Yeah, while sharing your screen, yes, while sharing your screen, if you can answer one of our viewers' question as well.
Yes.
Neha is asking, what is the difference between a square and a rhombus? I believe you just told us that there is some difference in the sides and angles or something. So
Yes.
while sharing your screen, you can just answer this question as well.
Yeah, that's exactly what I have kept as a suspense for you. So I just told you that we are going to ravel or unravel the mystery of a square passing through the rectangle and the rhombus. So I think I'll keep your question on a hold to tell you that you will discover it yourself in the course of the entire chapter.
Sure.
So Neha can hold on for a while.
Yes, sure, she can. And
I
we
hope
can go ahead.
Yeah, I think I have shared my screen with you and it is visible.
No, not yet. You do, I think, whatever you have to share your presentation if, so you have to keep it open and then share it with us.
Yeah, I'm
just share your screen again. Meanwhile, we will be learning about quadrilaterals. It has four sides, and then we have various types of, polygons with different shapes. Now we can see your screen.
Okay, thank you. Yeah, thank you.
Yeah.
So we are with the understanding of the quadrilaterals. So we move on. Now we are going to talk about plane curves. How do you get a plane curve? This is something which you know from your earlier classes also. A figure which is obtained by joining any points on a plane. The only thing you have to remember is you have to do this exercise without lifting your pencil. So there is some continuous curve that you have to draw. And because it is on a plane, we call it a plane curve. Now plane curves can be drawn on any sheet of paper also. Just make dots on a plain paper and then join them without lifting your pencil. What you will achieve will be a plane curve. Now there are classifications on these plane curves also. That is where that will lead us to the polygons. So one by one we will see how we can classify plane curves. Now in front of you I have brought 4 plane curves. Now these can be classified based on their shape and the way it is drawn. Now you can see I can classify these as open curve and a closed curve. Now the top ones are open curves, whereas the bottom ones are closed curves. Now how do we classify this? Now when you see an open curve, you see the starting point and the ending point are not the same. Here too, in the second one, see it starts from here, it goes on like this and ends at a different point. So such curves which do not have their starting and the ending point at the same place are called or classified as open curves. Now coming to the closed curve, you can see they start at a point and they end at the same point. That's why they are closed. Coming to this curve also, you start from here, you go on like this and come back to the same point. And because they come back to the same point, they are closed. So this is one way of classifying the plane curves. There is another way in which you can classify them. So I'll take the same 4 examples once again and show you that there is another classification which will work here. So those will be the simple curves and the not the simple curves. Like now here, the ones on the left hand side will be the simple curves, whereas ones on the right hand side will be not the simple curves. Now why are these called the simple curves? What's the difference? Now you can see it clearly that there is no overlap in the boundary for these 2 curves at the left. Whereas in the curves on the right side, you have an overlap in their boundaries. So that is why these cannot be called as simple curves. When there are curves which do not have any overlap in their boundaries, those are classified as the simple curves. So now we have been able to see what are open curves, what are closed curves, and what are simple curves. Now all these 3 are required for us to define a polygon. So next we are moving on to what is a polygon. Now we define a polygon as a simple closed curve made of only line segments. So that is how the circles are eliminated from this category, because we are talking only about closed curves made of line segments. So that's how in the concept map also I have shown you those curves which are not polygons will be categorized as the circles. Now here I have the polygons for you because all the 4 are clearly visible as polygons as they are made of only line segments. Now here I have a task for you. So you see that every polygon has got some vertices and the sides. Now what's the vertex of a polygon? It is the point of intersection of any 2 sides of a given polygon. So let me go and count the number of vertices the first polygon has got. So I'll just do it for you. It's 1, 2, 3 and 4. So this polygon has got 4 vertices. What about the number of sides? I'll just count it like this: 1, 2, a 3 and a 4. So this polygon has got 4 vertices and 4 sides. Now coming to the second one. Here also you have 1, 2, 3 and 4. These are the 4 corners or the 4 vertices of this polygon. What about the sides? Again I count 1, 2, 3 and a 4. So here also the polygon has got 4 vertices and 4 sides. Coming to the third one, it is very evident now. You will be quick in counting them now. So it is 1, 2, 3, 4 and 5. Because there are 5 vertices, definitely you will be counting 1, 2, 3, 4 and 5 sides for this polygon. Moving on to the last one, quickly we shall count 1, 2, 3, 4, 5 and 6 corners or vertices, and consequently there will be 1, 2, 3, 4, 5 and 6 sides for this polygon. So what can be generalized from this counting that we have done? We are able to see that in a polygon, the number of sides is equal to the number of vertices. So if I want to generally take any polygon and start counting its sides and the vertices, they will always come out to be equal in number. So that's how we call a polygon with n sides as a n-gon. So this is a general name given to any polygon having n sides and n vertices. But now I'm going to give you a nomenclature where you will be taken through specific names given to polygons with specific number of sides and vertices. So for which I'm going to my next slide. where I shall be showing you the nomenclature that is usually followed for all these n-sided polygons. So once I have 3 sides in a polygon, the name given to that polygon is a triangle. If a polygon has got 4 sides, you can come and see here that there are 4 sides and 4 vertices for this polygon, and this polygon is given a special name, which is the quadrilaterals. This is our point of discussion in this chapter. But to know further that there are specific nomenclature available for a 5, 6, 7, 8, 9 and 10 sided polygon. A 5-sided polygon will be called a pentagon. A 6-sided polygon is called a hexagon. A 7-sided, a heptagon. An 8-sided polygon is an octagon. A 9-sided polygon is a nonagon. And a 10-sided polygon is called a decagon. So this is the nomenclature that we shall follow as we take up these polygons maybe in our higher classes. But now we are going to confine our study totally to this 4-sided polygon, which we call the quadrilaterals. So now that we are going to confine our study to 4-sided polygons, I am going to introduce you to one more concept in the quadrilaterals. Now I am going to talk about non-consecutive vertices of a polygon. Now what do you understand by non-consecutive vertices of a polygon? Now when I say consecutive, it means they lie very next to each other, or in other words, they are adjacent to each other. But when I say non-consecutive, it is very clear that they are not going to lie very next to each other. Now why I am introducing this non-consecutive vertices is, now I am going to take you through a small activity where we will be connecting the non-consecutive vertices of a given polygon using line segments. And once we draw these line segments, we shall see what happens and what is that we are able to get out of it. So I think we will now go and try to find out what happens when we draw line segments connecting the non-consecutive vertices of a polygon. So for which again I go to my screen share, where I will be going to my...
Do the polygon have 11 sides as well?
Yes, we have
And
stopped
it
it.
is
That's why I
called?
said, generally it is called a n-gon. When it is having n sides, the nomenclature is restricted to a decagon for class 8. So we have stopped there. Definitely there are any number of sides.
One of our viewer is trying to say that hendecagon have 11 sides. Is that correct?
No, decagon is a 10-sided polygon.
Hendecagon.
Hendecagon. Yeah, I think that also can wait for a while, because we are going to totally confine our view to the quadrilaterals. Yes, your learning can continue. I am very happy that you are able to try to think and discover the names of these polygons. Very good.
Shows their excitement.
Keep going back. Yes.
Yeah.
Yeah, this is what I was talking about. In a polygon with 4 or more vertices, we can draw line segments to join their non-consecutive vertices. Why should I say only 4 or more vertices? This is very important, because in a 3-sided polygon, we will never end up with any non-consecutive vertex at all, because each one will be adjacent to 2 other vertices. So only when you have polygons with 4 or more vertices, we end up with non-consecutive vertices. And what we are going to do with these non-consecutive vertices? We are going to join them using line segments. So non-consecutive vertices are the ones which do not lie very next to each other. So now I have brought you to these 3 figures, where one is a quadrilateral because it has got 4 sides. The second one, you should be guessing it now. It has got 5 sides. So the name given here will be a pentagon. Again here it is a 4-sided one, but shape is slightly different. Still it will remain as a quadrilateral. Now why I have taken that, you will understand when I connect their non-consecutive vertices with line segments. So now in this quadrilateral ABCD, A and C are the non-consecutive vertices. Why? Because they are not adjacent to each other. B happens to be in between A and C. So A and C is one set of non-consecutive vertices, and similarly B and D is another set of non-consecutive vertices. So when I try joining them with line segments, this is what I end up with. That is, I have the line segments AC and BD drawn. Now coming to the pentagon, if I start with as E, F, G, H, I, when I start with E, F and I are the adjacent vertices, whereas G and H are the non-consecutive or non-consecutive vertices, because F and I become the consecutive or the adjacent vertices. So I have just joined them with line segments. Similarly, with respect to each of the vertex, I am trying to locate the non-consecutive vertex and connect them with line segments. And hence I end up with all these line segments, which I have listed here. Now coming to the fourth figure, here it is a quadrilateral. Again, the non-consecutive vertices happen to be J and L, and then the other set is K and N. So I have joined them using the line segments. Now when I try to join them using this line segments, the line segment that I use to join these two non-consecutive vertices of a polygon is called its diagonal. So what I have drawn in the previous slide is the diagonals of these three figures that I have taken. Now, why is this diagonal important for me? It is so because it will help me in classifying the polygons into two major varieties. This we have seen it in our concept map also. I was talking about the convex polygon and the concave polygon. Now, what's the difference? The difference is based on the diagonals alone. When all the diagonals of a given polygon lies within the given polygon or in its interior, then we call such a polygon as a convex polygon. Now you can see in these examples here, I have shaded them with a different color to make you understand the interior of the polygon. The colored region is the interior or the inside of a polygon. Now you can see all these dotted lines are the diagonals that we have drawn, and they all happen to lie inside the polygon, and hence these polygons are called the convex polygons. Now what if they do not happen to fall in the interior of the polygon? Now that's why I have taken these two examples. Again, these two are polygons. You can count the number of vertex and find out on your own what is the name given to these polygons. Now what I want you to concentrate here is one of its diagonals in both these figures happen to be outside. That is, they are in the white region. Can you see that? The shaded region is the interior or the inside of the polygon. Now here in this, you see that at least one of its diagonals is happening to be on the exterior, and hence such polygons are called the concave polygons. So this is how the classification works. To make this classification, what we have learnt is the diagonal. So what's a diagonal? It is the line segment joining any two non-consecutive vertices of a given polygon. Now there is another way in which you can classify polygons, not only just based on its diagonals. Now we are going to concentrate on its sides and its angles. Now I have two polygons in front of you. You can just observe them for maybe 10 seconds and tell me if there is a difference. Yeah, what I can guess is that you are saying that all the angles and the sides in the first polygon are not the same. They are different. You can see that's why I have labeled all of them. But when you come to the second polygon, you see that their angles as well as their sides are equal. So there is this classification which has come in now, which we call as the irregular polygon and the regular polygon. So if a polygon has got equal sides and equal angles, such polygons will be classified as regular polygons, and those which are not having equal sides and equal angles will be called irregular polygons. So that's how the definition works. I'll just quickly read. A polygon which is not equiangular or equilateral. Equiangular, not having equal angles. Not equilateral means not having equal sides. Is called an irregular polygon. But a polygon which is equiangular and equilateral is called a regular polygon. So now we have totally confined our study to four-sided polygons. We are into quadrilaterals. So we are moving on to the first exciting property of the quadrilaterals, which is called the angle sum property of the quadrilaterals. Now I'm going to just arbitrarily take any quadrilateral ABCD and try to measure its angles. So this is the quadrilateral that I've taken, and I've tried to measure the interior angles, and I've labeled it here for you. Now when you add all these angles, just see what happens. Maybe you can quickly add it yourself and find out. Now I'm seeing that it sums up to 360 degrees. So now my question is, if I take any quadrilateral, is this going to work? So to show this to you, I'm just taking you to a GeoGebra app. So I'll have to stop my screen share here and come back to you. So one specific quadrilateral, we have seen that the sum of the interior angles has become equal to 360 degrees. Now the question for us is it going to remain the same for any quadrilateral that I take? So to answer that question, I'm going to take you into the GeoGebra app. I think I have shared my screen. Are you seeing my screen? Yeah.
Yes.
Yeah, thank you.
We can.
Yeah, so this is another quadrilateral with the angles I have marked as alpha, beta, gamma, and theta. You can see that the measurements are added here and it sums up to 360 degrees. So this is one particular quadrilateral whose angles, interior angles, sum up to 360 degrees. Now I'm going to see, is it going to remain the same when I change the shape of this quadrilateral? So I'm just going to pull this vertex A and just keep observing what happens to the angles there. Can you see that there are changes in the angles happening, but what is remaining the same? The 360 remains the same. However, you change the length or the angle in the quadrilateral, whatever shape you give to the quadrilateral, you can clearly observe, though the angles are changing rapidly, but still the sum always remains 360 degrees. So this is an excellent app which is making you see just in front of your eyes that whenever you try to change the angles, the interior angles of any given quadrilateral, the sum will always remain 360. Even you can bring it to the shape of a rectangle or a square, which is very well known to you, because you know in a rectangle or a square, the angles are all going to be 90 degrees and then they'll sum up to 360 degrees. So I have almost reached 90. If I make a little more adjustment, maybe I can get a quadrilateral or a rectangle or a square from it, and hence there also it can be verified. So now this was an activity which I have done for you. Now I have an activity which you can do yourself and try to verify the same property, but in a more exciting way, for which I think I have to stop my screen share, come back to you and take you to that activity. So I go and share my screen again.
So we saw the GeoGebra app, which clearly defines that all the angles total make it 360 degree. And now an activity for our students so that they can also test this and learn this by doing something on their own.
Yeah.
Yes, Ms. Harini,
Yeah,
you can go ahead.
Just going to my slide. Yeah, this is a paper cutting activity to verify the angle sum property of the quadrilateral. So this is something that you're going to do on your own. I'm just giving you a small guidelines of how you can do it. So what is the first thing that you have to do? You have to draw any quadrilateral of any size or shape and get ready with the quadrilateral. And you're seeing that the quadrilateral is blue in color, but you have 4 different colors on the corners. Now these are the angle caps that we have made for the 4 interior angles. If you think making an angle cap is going to bother you, don't worry at all. It is just a trace of this angle that I have made in a different color. If you think doing that will be difficult, you just need to cut the corners of this quadrilateral and take it out. What you will get is those 4 interior angles that you will have. Now what should I do with these cutouts? The next step is, when you arrange them like this, around a point, they will exactly beautifully form a circle. So what that conveys to you is the total angle, that is A plus B plus C plus D, is going to become 360 degrees. How? Because angles around a point definitely form a complete 360 degrees. So when I cut these pieces and keep it adjacent to each other, they will beautifully form a complete circle. So that is how you verify the angle sum property by doing this paper cutting activity. And hence, you will be able to tell that the sum of the interior angles of any given quadrilateral will be equal to 360 degrees. Now the next question is, if I am to generalize this for any n-sided polygon. Now it was a quadrilateral, so we had only 4 vertices and 4 angles that we had to combine and see like this. Now as the number of sides and the vertices of a polygon is going to increase, do you think you will be able to do this activity like the way you did it for the quadrilaterals? So there also I am going to help you with a small general formula which will help you to calculate the angle sum property of any n-sided polygon. For which, again, I go to my next slide. So I have four different varieties of polygons in front of you now. So that is the triangle, which is the first one, ABC. DEFG is a quadrilateral because it is a four-sided polygon. The next one is a pentagon, which has got 5 vertices, and the last one is a hexagon with 6 vertices. Now we are going to try to generate a general formula which will allow me to find out the angle sum property of any n-sided polygon. So this is also quite interesting. We are going to generate a formula, means we are going to intuitively find out if there is any way we can use in a simple way to get the angle sum property for any n-sided. We don't have to go and do any paper cutting activity to go and see whether it sums up to a particular angle or not. So for a triangle, we all know that the angle sum property, that sum of the interior angles of a triangle is going to be 180 degrees. Now in the second one, that is the quadrilateral, which we have just now seen, we have found that the angle sum property is 360 degrees. Now how can I look at this in terms of triangles? That's exactly which is going to give me the clue to generate that formula that I'm going to apply. So what do I do to divide this quadrilateral into two triangles? What did I do? I just had to draw this diagonal. Once I draw one of the diagonal of this polygon, I have divided them into two triangles. Now, the sum of these four angles, that is D, E, F and G, will be nothing but the sum of the angles of the first triangle, that is DEG, and the sum of the angles of the second triangle, which is EFG. So if I add all the angles of the first triangle with all the angles of the second triangle, what I will end up with is the angles of the quadrilateral. So by drawing the diagonal, I have made two pieces of the quadrilateral, each one of them is a triangle. And hence I am applying the angle sum property of the triangle 2 times here to get the angle sum property of the quadrilateral. The same rule can I apply it for a pentagon. Now here I have to draw two diagonals to split the pentagon into 3 smaller triangles. So when I have these 3 smaller triangles, I know the first triangle, the angles will sum up to 180. In the second triangle, again it will be 180. And in the third triangle, again it will be a 180. So it will be 180 plus 180 plus 180. Or in other words, 180 multiplied by 3 will give me the angle sum property for a pentagon. Now coming to a hexagon. What did I do? I had to draw 3 diagonals here so that I have split my entire pentagon as 4 smaller triangles. So when I divide them into 4 smaller triangles, what do I understand? All the angles in this first triangle plus all the angles in the second triangle plus the angles in the third and the angles in the fourth triangle will totally sum up to the interior angles of this hexagon. And I know each of these triangles will sum up to 180 plus 180 plus 180 plus 180, which in other words is 4 times 180, which will give me the angle sum for a hexagon. So I am in the process of generating a simple method to find the angle sum property of any n-sided polygon. So using this idea of splitting any given n-sided polygon into triangles and trying to find out what will be their angle sum, I end up with such an observation. Suppose the polygon that I have taken is having just 3 sides. I know a 3-sided polygon is a triangle. So I make this formula as 3 minus 2 into 180 will give me the angle sum for a triangle. 3 minus 2 becomes 1. So 1 into 180, the angle sum for a triangle will be 180 degrees. So moving further, whether I am able to generalize this for all other n-sided polygon is what I have to verify. Now if I have a 4-sided polygon, which I call it as a quadrilateral, can I take it as 4 minus 2 times 180? So 4 minus 2 I know will become 2. 2 multiplied with 180 is going to become 360 degrees, which we have verified very much in our previous activity. Now when it comes to a pentagon, can I take it as 5 minus 2 and tell it is 3 multiplied with 180, which will give me a 540 degrees. So I am able to see that when I take it as 5 minus 2 multiplied with 180, I get the angle sum for a 5-sided polygon as 540 degrees. So when it is a hexagon, again, when I apply this rule of taking the number of sides as 6, 6 minus 2 into 180, which will be 4 into 180, and hence it becomes 720 degrees. So with this kind of verification that I have done, now I can generate a formula which will allow me to get the angle sum for any n-sided polygon. So if I have n sides in a given polygon, I take it as n minus 2 multiplied with 180, which will give me the angle sum for any n-sided polygon. So that was exciting, is it not? Because we are able to get a general formula which will allow us to find the angle sum property of any given n-sided polygon, where n is the number of sides for any particular polygon that you have taken. So this is all that we had to see for this portion of our quadrilaterals. So we will have to continue with our next class, where we will be taking or classifying quadrilaterals based on their properties. So this is how I want to stop this lesson here, because the next portion is only quadrilaterals based on their properties. So this is the final thing that I have, that the sum of the interior angles of any n-sided polygon is given as n minus 2 times 180 degrees. So I hope you thoroughly enjoyed the class. Thank you for your patient hearing. I hope we will get to see each other in the next class. If I have
Of course, but there are a few questions, Ms. Harini, from our viewers as well. Maybe it would be like a revision for our students, whatever we have taught today. But Ms. Ananya wants to understand the difference between a convex and a concave polygon. If you can just help us.
Yes. Can I go back to the slides? Maybe I can show her.
That will be a good idea.
She is able to. Okay, I may have to share my screen again.
Yeah,
no, I'm in the
screen, we can see your screen.
Yeah, right.
Just go to the particular slide which you want to show.
Yeah. This is a convex polygon. Why this is a convex polygon? Because all its diagonals are in the interior of the polygon. What is a diagonal we have discussed? It is a line segment which joins any two non-consecutive vertices of a given polygon. So when I tried drawing all the diagonals of this polygon, I have seen that they are all clearly within the polygon itself. So such kind of polygons we classify as the convex polygons. Then we come on to the next figure. You can see that at least if one of its diagonal happens to be on the exterior or outside the given polygon, then such varieties of polygons will be called the concave polygon. I hope it is clear now. That's why I had even told that I have shaded the interior. Yes. This is the actual region of the polygon, this yellow colored region. And you see this diagonal IK is on the outside. It is not inside the polygon, and hence this will be categorized as a concave polygon. Similarly here, this diagonal is on the exterior. You can see it. It is not inside the polygon, and hence this is also another variety of a concave polygon. I hope I'm clear now.
Yes, another viewer of ours, Ms. Manjul, wants to understand how to find out number of diagonals of a shape.
A shape, we are only talking about plane figures here. Maybe when we go on to a shape, that is the next part of the geometry that we have, maybe we will clarify that there. Because we are not talking about shapes here, we are talking only
about the plane figures.
Yes.
We got it. Okay. Last question for the session. Can a parallelogram be a trapezium as well?
That's what I'm telling you. See, we are going to go through the properties in a very systematic manner. So I think this question also can be kept on a hold, because I don't want to answer and reduce their curiosity here.
Of course.
It will be taken through the entire journey of all varieties of quadrilaterals based on their properties. So I don't want to spoil that learning here. So I leave that question unattended for now. I am very hopeful that with the progress of the next part of the session, they will get all their queries answered on their own without my intervention at all.
Okay, fine. Thank you so much for joining us today, and we'll see you in the second part of this particular session, which will be coming up very soon.
Yeah, thank you. Namaskar.
Yeah, that's all for this session. Your questions are with us and we are going to answer them definitely. We'll be taking these questions again in our next session from Ms. Harini on quadrilaterals, and I'm sure you'll get to know all your queries solved. And if you have any more queries, you can get in touch with us with our email address ciet.kishoremanch@gmail.com. You keep posting your questions. We'll try to answer all of them. Thank you so much for joining us. Namaskar.